can start.
Thank you very much for introduction. So I will start the tutorial about security of quantum key distribution. So I'm Masato Koashi from University of Tokyo. So, this is the overview of quantum key distribution, and I'll send some weak light pulses to Bob, and Bob makes a measurement, and they accumulate the shifted key. Then they correct errors and also do the privacy implication to arrive at some final key here, and they hope that this final key is secret from eavesdropper here. And aim of this tutorial is to explain how we can prove the security of QKD protocols against general attacks, focusing on the approach with kind of phase errors or phase error correction, which dates back to Meyers or Shor and Preskill. So I divided my tutorial to two parts. And the first part is about methodology of this method. So I will explain in 3 steps here. Then I will give you the application of this method to various protocols listed here. So, okay, let's start to the step 1. So the goal of the QKD is to create the final key, and the ideal property of the final key is summarized as these 3 properties. So there's no correlation to Eve, and distribution is uniform, and also there's no error between Alice and Bob. And it is convenient to describe Alice's key and Bob's key in Eve's quantum system in a single quantum state like this. So general state will look like this. So here, because Alice's key and Bob's key is classical objects, so we can describe by using some orthogonal basis here. Then Eve's quantum system may depend on key value in the general state. But the ideal state satisfying these conditions is look like this. So here, decoupled from Eve, and key value is also the same, always the same, and also the probability is the same. So this is the ideal state. So this is the goal of quantum key distribution. Now, it is convenient to divide this security condition to 2 conditions. So one is secrecy for Alice. So just care about Alice's key and forget about Bob's key. So we are talking about the state for which the Bob's key is traced out. So it's a property of state AE here, and the ideal state looks like this. So this is the secrecy condition, and the correctness is just this condition here. Now, if 2 conditions are met, then that means that the overall security is satisfied. Now, the starting point of the phase error approach is actually considering in what situation are we sure of achieving this ideal state between Alice's key and eavesdropper's quantum system. So, obviously, if you prepare a qubit on the X basis eigenstate, then make a measurement on the Z basis here, then this bit would be truly random. Okay, so this is because this state is pure state. So pure state should have no correlation to other systems. So if you do this measurement, then you have a perfect 1 bit of key here. So you can easily generalize this to have K qubits in a prostate here, then make a Z basis measurement. Then surely you would have this ideal state here. Now, let me add some operational flavor to this statement. So if you measure these qubits in the X spaces here, then outcome would be all 0. So let me define the outcome all 0 as success, and any other outcome to be a failure. Then this can be rephrased in such a way that if there is a promise about this state, such that if you do this measurement, the failure probability is 0, then this final key is perfectly secret. Okay, this is almost trivial, but I will gradually extend this notion to cover the security of QKD. So this is, of course, this theorem is too weak. So Alice would have an objection, and also Bob would have complaints. But these complaints should be settled by the introduction of entanglement. So what the Alice's complaint is that if she look at her sender and her transmitter, she doesn't find any qubits here. So normally the transmitter, in the transmitter, say the random number is first drawn, and according to this random number, quantum state is generated and sent to above. But you can always replace this by equivalently by introducing entangled state, which is a superposition of this possibility and this possibility using the fictitious qubit here. So Alice can create this entangled state first, then measure this qubit in the Z basis to obtain the bit value. So this and this is completely the same thing. So you can always introduce a qubit like this. Now, what about Bob's complaint? So Bob complains that this is secret also from Bob, so it is useless. So in order to answer to this Bob's question, say we must slightly extend this theorem, tiny theorem, a little bit. So observe that if we rotate these qubits just before this measurement, the basis measurement, then the outcome would be the same. So what I mean is that the final state here and the final state is here if the rotation is along the z-axis here. So what I mean is that the operations that commute with z observable for every qubit. So maybe I should say the preserving operations, because this includes not only the rotation, but also some controlled unitary operation from these qubits. So anyway, because the rotation doesn't change this state, we can apply this tiny theorem here, then we obtain this. So showing the failure probability is 0, we are allowed to do any z-axis rotation before that. So we can freely do this to reduce the failure probability, okay? Now, let us introduce entanglement. So suppose that Alice's qubit here is entangled to Bob's photon in this maximally entangled state. Then if Bob make a measurement to distinguish these two polarizations here, then surely Bob would obtain Alice's final key here. So protocol achieves correctness. Now consider what Bob could have done here. So instead of doing this, Bob could have measured this photon to distinguish these two diagonal polarizations. Then Bob would know this qubit is pointing right or pointing left. So then Bob can give instruction to Alice such that Alice should rotate this qubit and also rotate this qubit, such that all qubits are reset to the value 0. So this means that if we start from the maximum entangled state here, then Bob can do this task completely, perfectly. So this means the secrecy for this key here. So this gives that, say, if you start from a perfect entangled state, actually you would have a perfect secret key. So in the real protocol, Bob tries to guess Alice's final key, but we argue that Bob could have tried to help resetting Alice's qubits to 0 on X basis. And if this can be done perfectly, then this implies that the actual final key here is ideal. It's perfectly secret. Now, maybe you feel that this is just rephrasing that you can create perfect secret key from maximum entangled state. And that's true if you confine this communication here to a classical channel. Then the fact that both tasks are perfectly feasible is equivalent to sharing k bits of entanglement. But this notion here does not have to limit the channel to be classical. So the same argument works if we allow quantum channel here, or if we allow Alice's other systems to be involved here. So the most general statement is that if there is a promise that failure probability is 0 after some doing z preserving operations here to resetting Alice's qubit to 0, then this binary key is secure. So if you are familiar with a state called gamma state or shield, then actually this operation here is a kind of rewinding or unlocking the shield to recover the maximum entanglement state. So this is the kind of most general description of having a perfect secret key. Okay, so let me make some remark about this. So here, Bob has two choices of tasks, but these two tasks are obviously mutually exclusive because here, Bob learns the identity of Alice's final key, but here, Bob actually erases any information about Alice's final key in not only in the Bob space, but also in the everywhere except Alice. So obviously this task and this task is mutually exclusive tasks. So appearing this pair of tasks which is mutually exclusive is a property of complementarity in quantum mechanics. So in this sense, this phasor approach is connecting the property of secret key to the quantum property of complementarity. Okay, so this is the story about when there is no errors. So next, I would like to introduce the small errors here. So we want a theorem looking like if there is a promise that the failure probability here is not exactly 0, but a small number, then we want to say somehow the final state here is close to the ideal state. So we're talking about how close this state is to ideal state. So what is a proper measure of closeness? Then there is a standard measure used in the QKD, which ensures the universal composable security. So the point is the measures distance between the two mixed states by using trace distance, which satisfies monotonicity and triangle inequality. And specify this state, if state in the ideal state, to be the same as the real state here. So this equality holds. So always compare the ideal state with this state equal to this one. Okay. And the third one is, this is kind of academic one, but regard system E to be not just an adversarial system, but regard E as everything, every word. And as long as you're proving security against general attacks, then you don't have to worry about this difference, because if you can prove that, then you automatically include everything as a system E. So what I meant about composable security is this. So please recall that actual QKD protocol produces final key and also outputs something like a key length or some public announcement, and also eavesdropper attacks the quantum channel. So there is some quantum interaction here. And let us define ideal QKD protocol here in terms of this actual protocol. So this is actually embedding this actual QKD protocol here, but to just discard the real key here and instead create ideal key, then output this. So difference here is replacing the real final key to ideal key. And let us consider the difference between using actual protocol and ideal protocol. So let us define this state, and this state is the state of everything after carrying out this protocol and this protocol. Now the definition of epsilon security is like this. So the protocol is epsilon secure if it is guaranteed that the trace distance between this state and this state is no greater than epsilon. Then this is a kind of very strong statement. So because due to the monotonicity here, say for any event in the future, a probability of event when actual protocol is used and probability of the same event when ideal protocol was used is almost the same probability, which is bounded by this epsilon. So this event can be something like your company faces bankruptcy, or anything can be applied to this statement. So this is pretty much strong statement. So in particular, in the case of quant QKD protocols, an actual state is related to this state already defined here. And ideal state is related to the state where only the key part is replaced by ideal key. So this is why I insist that ideal state and real state and ideal state should have the same same reduced state of the system. Okay, so actual state was given by some average over the key length k here, and the ideal state is given by this. So the epsilon security in the QKD protocol is look like this. So trace distance is smaller than epsilon. Now, a good thing about this measure is that it can be composable. So sometimes we want to measure the imperfection of the case where there are two or more protocols are used at the same time. Then you want to compare the ideal situation. But you can always argue that you can make the intermediate situation like this. Then you compare this and this. Then definition of epsilon security assures that the distance between this and this is epsilon prime. Then you compare these two. Then due to the definition of the epsilon security here, distance between this state and this state here is epsilon. Then, thanks to the triangle inequality, you can easily see that the trace distance between this state and this state is bounded by the sum of the imperfection. So, thanks to this, you only have to prove the epsilon security of each of the protocols. Then, the combination of protocols are automatically handled. Okay, so in the ideal case, I separated the whole condition to secrecy for Alice and correctness. And a similar thing can be done for this epsilon security. So you can define the epsilon secrecy for Alice, which only concerned about Alice's key. So forget about Bob's key, but use the same similar condition here. And also you can define correctness. So epsilon correct to be the error probability to be no greater than this. So if we define like this, then you can easily prove that if this is true and this is true, then actually the protocol is epsilon secure with epsilon equal to the sum of this imperfection and this imperfection. So this can be easily proved if we consider this kind of intermediate state. Okay, so what we want the theorem looking like, if there is a promise that the failure probability of this protocol is small, then the protocol is epsilon secret. So remaining thing is that the relation between this small number and this small number. But fortunately, this is a very simple relation. So if this is delta, then actually the protocol with the square root of 2 times delta secret. Now the proof of this is a little bit involved. So actually I have written down here, which takes 3 slides. So I'm not going into details here, but I would like to mention why this square root. So square root appears here. Square root appears here. So this is because this failure probability here is written as a fidelity of this input state to the ideal state. Ideal state is all the plus states here. So this quantity is a kind of fidelity of states. So at the end of the day, fidelity of actual state and the ideal state is given in terms of this delta here. But a final statement about epsilon secrecy is given by trace distance. So you must connect fidelity to trace distance. And the only thing we can use is the general inequality here. It is famous inequality, which involves square root here. So this square root appears because we changed the measure from fidelity to trace distance. Okay, anyway, if we consider small imperfection, then say if Bob can help Alice to resetting these qubits to the plus state, if the failure probability is delta, then protocol is the square root of 2 delta secret. Okay. Then next is the practical case. So this scenario I just think this scenario here would work if entanglement distillation is actually carried out, but normally we don't do that. So what happens in the realistic cases is that even if Bob tried to help Alice, Alice cannot reset these qubits to prostate. So this outcome involves some ones. So I define each of one here to be phase and phase. So in this case, this protocol almost always fails. So this means that this key bit is insecure. So in this case, this key is not the final key. So this key is called shifted key. And in the actual protocol, of course, we do the privacy amplification to convert bits to a smaller number of bits. So what we want to prove the security of this final key, what we want is that say we have some promise on statistical property of the phase errors, so occurrence of ones here. For example, the number of phase errors, number of ones here is bounded by some constant, except a small probability. So if you have that kind of promise, we want to prove that this final key is epsilon secret. But this is our goal. Now here in this talk, I assume that Alice helps Bob by sending some number of bits of encrypted message for Bob to do the error correction. So this consumes many this bits of secret key. So net key gain of the whole entire protocol would be the final key length minus this consumed bits. So I assume this because I want to separate the argument of error correction from the privacy amplification. So this is not mandatory, but in this talk I assume this. So forget about this error correction part. Okay, so what is the privacy amplification here? So privacy amplification here is that actually the multiplication of some binary matrix to the shifted key bits. So privacy implications, calculation, computation look like this. And here we are considering the shifted key is the Z-basis outcome of the same number of qubits. Now, at I think this point is a good point when I should mention about another approach to the security of QKD, or the other approach. And this is called leftover hashing lemma, started by Leonardo Rena. So in this approach, actually, we are looking at the correlation between this shifted key to the Eve's quantum system, and somehow quantify the correlation in terms of conditional mean entropy. Then if you have a lower bound on this quantity, then there is a leftover hashing lemma, which tells you about the security of the final key. And here, in the phase error correction approach, say we are looking at correlation of these qubits to Bob's quantum system in terms of phase error, statistics of phase errors. So we want to connect the statistical property of this, connect correlation with this to security of the final key. And if you are interested in relation between two approaches, then I refer to this recent paper by Dr. Tsuruma here. Okay, let us continue with the phase error approach. So first thing is rewrite this classical computation to a quantum operation. So we want to do this by using a quantum gates. So this can be done by just extending this matrix to a square full rank matrix. Then multiplication of this matrix can be easily represented by a bunch of control NOT gates. So we can easily create the quantum circuit here. Then we just discard these qubits and only look at the k qubits here and make a measurement on the Z basis. Then we obtain the final outcome here. So this is equivalent to this, okay? Now, what can we say about this quantum circuit? Maybe many of the audience will be familiar about the property of control NOT gate. So a control NOT gate on some basis, Z basis, for example, is equivalent to another control node gate on the X space. So if we change the basis, then the control gate actually the target and control is replaced to each other. And this is actually generalized to any matrix here. So control node operation is a operation of this matrix, but on the X basis, this is equivalent to operation of this matrix. But even if when this matrix is larger, dimension is larger, still, if this matrix is C, then this matrix is given by its inverse and transpose. Now using this, if this quantum circuit is written like this in the D basis, then that means that if we switch to the X basis, the same quantum circuit actually compute the multiplication of another binary matrix here. So the pattern of pointing right and pointing left will be transformed into another pattern, which is corresponds to this computation. Now, because these qubits are discarded, why don't we measure these qubits along the X spaces? Then this outcome here is a kind of clue about what the true pattern here is. What I mean is, let's say this bit is the inner product of this row and this true pattern here. So this bit tells you about some clue about this true bit string here. And also recall that we have some promise about this pattern here, like the number of phase errors, number of 1 here is bounded by some constant number, something like this. So we have some initial knowledge about this sequence, and we have some clue here. Then combine these two, maybe we can identify this string perfectly. Then actually we know the pattern here of these qubits. So that means we can rotate these left pointing guys such that if we measure these qubits on the X basis, then surely the outcome will be also. So if we can do this with failure probability smaller than delta, then this means that the final key after the private simplification is ipsum secret, like this. Okay, so this means that the private simplification to shrinking the n bits to k bits on the Z basis is actually, if we look at the same thing on the X basis, then it's the phasor correction, somehow the same resetting the phase errors to all zeros using the n minus k bits of hints here. Now, what about the amount of private simplification? So what about the length of the final key in terms of this initial promise here? So suppose that number of possible phasor patterns, so possible this string is upper bounded by some number 2 to the constant number. For example, if there is a promise that the number of ones upper bounded like this, then this constant is given by this n times binary entropy of this ratio here. Now, we start from this number of candidates, possible candidates, but every bit here would have the number of candidates here. So repeating this measurement n minus k times, then if this inequality is satisfied, then all the wrong candidates will be eliminated. So this means that if this inequality is true, then roughly speaking, this failure probability would be small. So the key will be secure. So the final key length here is n minus actually this quantity here. This is a rough sketch. And if you want a precise statement, then suppose you can choose a candidate set P of probable phasor patterns such that true patterns here belongs to that set, except the small failure probability here. And the size of the set is bounded like this. And suppose that you choose the final key length k according to this number such that n minus this number and the slightly small. So this is a positive integer. Then every wrong candidate in this set would be eliminated by these clues, except probability, this small probability. So this is surely true if this matrix is chosen in a uniformly random way. But actual perhaps application is that it doesn't do that. So that's just pickups from small candidates of matrices. But still, this condition holds if the choice of this matrix is a universal too. So anyway, if this is the case, then actually the possibility of failure here is only two cases. One case is that the true number here does not belong to this candidate set. Then it would fail. That probability is delta 1 here. And another possibility of failure here is that the one wrong candidate survives this elimination process. That probability is that the probability of survival times the number of wrong candidates. Actually, it's this number minus 1. Okay. So the entire failure probability is bounded by this number, but substituting these numbers, we obtain this. So you end up with a formula that final key is 2 delta secret with delta being this number. So this can be made small, and this is also always can be small. So you can make your final key secret as good as you want. So this is summarize the point. So in the actual protocol, privacy amplification is done to shrink to the qubits, but Bob could have done something to help Alice to reset these qubits to reduce the number of phase errors here. But if there is if you can find this kind of promise here and setting the final key length like this, then you automatically have epsilon secret of the final key with epsilon being this quantity. So this gives the recipe for proving the finite size security for against a general attack. So I summarize the recipe here. So first, rewrite your quantum protocol, QKD protocol, such that Alice's shifted key is the z value of qubits here. Okay. Then in actual protocol, Bob do some measurement, but to find what Bob could have done to help reducing the phase errors in this basis. So here, you must be careful that this new measurement here must be compatible to Bob's announcement. So what actually announced by Bob in the actual protocol. So anyway, you only have to find one protocol here. Then if you determine the protocol here, then you compute the bound on the number of phase error patterns appearing here. Sometimes you can just bound the number of ones here is enough to bound the phase error patterns. Then you would obtain finite security here. So this is the recipe in this approach. And I would like to make a few remarks here. So in the asymptotic limit, sometimes people are saying about phase error probability or phase error rate. And the precise meaning of this quantity is like this. So you can bound the number of phase errors to be this value. So some slightly larger than n times phase error rate. And also this inequality is true except small probability. But you know that these two quantities converge to 0 in the limit of large n. So sometimes in the asymptotic limit, you don't know the explicit functional form of these two guys, but you only know that this converges to 0. But that's enough because in that case, asymptotic key rate is given by just this number here. Key rate, or efficiency of privacy application here is given by this number here. So finding this phase error rate is enough to achieve the asymptotic key rate. So, and another remark here is that it's a tagging technique called tagging. So sometimes you would find some qubits are higher probability of phase error, and some qubits are lower probability of phase error. In that case, you can argue that each qubit are somehow tagged, and you can classify the qubits according to the tag and assign different phase error probability. So in that case, actually, the number of phase error patterns is given by the product of each patterns, which means that this number is the sum of each tag value. So which end up with the k over n to be 1 minus average of binary entropy of each phasor probability. So this technique is often used in the proof. Okay, so this is the general recipe in the phasor correction approach. Okay. So this is the first half of the protocol. And in the latter half of the protocol, I will give you some examples of quantum QKD protocols. Okay. So first protocol is the BB84 protocol. So in the case, I consider ideal BB84 protocol using a single photon here. And I assume that this polarization is solely used for the signal, and the diagonal polarization is solely used for the test. Now, as in the prescription, you rewrite this as a entanglement state like this. And this is also written like this. So Alice's phase value here corresponds to diagonal polarization here. And Bob, in the signal, for the signal, Bob tries to distinguish these two states, and for the test, Bob tries to distinguish these two states. And I assume that the detection probability has no dependence on the basis for any input. Then we consider this template here. So this is actual protocol. So Bob do this measurement. So we consider what Bob should do in order to reset these qubits to 0 state, plus state here. Of course, the answer is distinguish these diagonal polarization. So good answer is to use the measurement exactly the same as the one used in the test mode. Then phase error in the signal mode happens when Bob has an error in discriminating these two diagonal polarizations, but that error is exactly the same as the error in the test mode. So phase error and error in the test mode is exactly the same thing. So this means that signal mode, phase error in the signal mode and the test mode is just fair sampling. So in the asymptotic, if you're concerned about asymptotic Q length, then you can just apply the observed error rate in the test as a phase error rate here. So this is asymptotic Q length. And if you want finite size security proof, then because this is just a fair sampling, say classical sampling theory is enough to bound the number of phase errors in the signal. So you can probably use simple random sampling, which is more famous. But personally, I recommend to use Bernoulli sampling here, in which each sample is drawn with a fixed probability P. This is because if you look at the actual protocol, actually signal and test is effectively chosen by a fixed probability. So situation is closer to this Bernoulli sampling. And also in this sampling, you can always have to handle binomial distribution. It is easier than considering hypergeometric distribution. Okay, anyway, in this case, the finite size security proof is also easy to be done. Okay, and okay, so I will skip this. And let me move on to B92 protocol. But before that, I will concentrate on the signal part of the B92, because this signal, binary phase encoding of the coherent states, is common to many other protocols here. So in this encoding, say bit 0 is coded to a coherent state with amplitude plus alpha, and bit value 1 is encoded on minus alpha. And the difference from the BB84 case is that this state 0 and this state 5, these states are not orthogonal to each other, non-orthogonal. So if you write down the entangled state between qubits in the right pulse like this, and if you switch to the X spaces here, then actually this coefficient would be different from this. And if this is a coherent state, actually we have here the Schrödinger cat state. So for the plus state, we have even Schrodinger-Cat states. So photon number is even, and here odd number Schrodinger-Cat states here. And even though I like 2 photons here, but the main contribution for this state is actually vacuum state when alpha is small. And for this coefficient here, this S alpha coefficient is defined like this. And if alpha is small, it's almost equal to alpha squared, which is the probability of having single photon here. So the probability of having minus state in Alice's qubit is almost equal to probability of emitting single photon here. Okay. So this is a property of signal used in many protocols, including B92 protocol. And in the case of B92 protocol, a measurement is look like this. So B92 measurement is 3 outputs, bit 0 and bit 1 and the failure. And this measurement is constructed according to expected amplitude. So Alice emits amplitude alpha, but the channel transmission with ether, that means the received amplitude would be beta defined like this. So ideal state received above is plus beta or minus beta. So this measurement tries to distinguish between these 2 states. And this measurement is kind of a null measurement. So this outcome excludes the possibility of input states to be a minus beta state or something like that. And the actual implementation is to shine your photon detector with a local oscillator with amplitude plus beta. In this case, if the input state is minus beta, then interference completely cancels this light. So this detector should not click. So that means that if this detector clicks, then the incoming state is not minus beta. So bit is not 1. So you are sure that the original bit value is 0. So this is the idea in the B92 measurement. Now, you see the template here. So you have entangled state here, and above that's B92 measurement. And let us consider what we should do in this X-basis protocol. So what Bob wants to do is distinguish between even state and odd state here. So one possible choice is to define this measurement as detecting this odd cat state. So if this state is coming in, this bit value is 1. So Bob tells Alice to rotate this qubit. So if you pick this kind of particular protocol here, then you can analyze the phase error probability. So this is not so simple, but here you can choose the orthogonal basis composed of even cat state, odd cat state, and others. Then actually, if Eve chooses other states here, then this has a high probability of bit error. So in the optimal attack, this portion would be never used. So important Hilbert space is only 4 dimensions, so spanned by this and this. And due to this correction rule, these 2 pair has no phase error, and these 2 pair has phase error. So you want to bound the amount of phase error here. And you can use the clue obtained in the test phase. So you can use the amount of bit error. Now, the observable of bit error actually depends on the coherence or superposition of this state and this state. So you must consider a qubit state formed by these 2 bases. So this is the kind of bromosphere. Then actually bit error is in this direction. So here another qubit, another bromosphere, and bit error is in this direction. And this green direction here is the probability of finding minus state here. So that probability is in this direction.
Yeah, it seems like we have lost Masato.
Yeah, I think I also lost.
Yeah, I think he'll probably be back soon.
Yeah, I think he's reconnecting.
Yeah.
You're on mute, yep.
Yeah.
Yep. So can you see that?
Yes.
Okay.
Yes.
Okay. So if bit error is 0, then you only 2 states is possible. And another condition is that the average of having minus state here, probability of having minus state here, must be the same as the initial value, because Eve cannot touch Alice's qubit here. So this means that average of this and this must be along this on this line here. So this determines the weight of this and this. So this completive determines the bit error probability. Oh, sorry, phase error probability here. So actually, if you compute this one, then you end up with this quantity, which is consistent with beam splitting attack. And if you want to analyze the generalized case with a positive bit error, you must do some numerics. So you must solve the problems. So given bit error probability and detection probability, compute the worst phase error probability. Now this sounds like difficult, but this is just a qubit, so 2x2 matrix, so the calculation is not so difficult. And if you want to finite-size security, in this case, you cannot use classical sampling theory. You must use something beyond that, and often people use Asimov's inequality here. Okay, so next protocol is the twin field QKD. And okay, so the advantage of this twin field QKD is that the achievable distance is almost doubled, like this. And why it is doubled is because whenever this Charlie detects a photon, then either Alice's photon reaches here or Bob's photon reaches here. So a photon travels only half the distance between Alice and Bob. So this is the reason why this protocol achieves the long distance. Now, today I want to talk about the security proof of this twin field type QKD. And since I'm talking about this binary signal, I want to pick up the variant of this phase twin field type QKD, which is called phase matching protocol. So here, Alice chooses this signal, and Bob also uses this signal and sent to central station. So in this case, actually Bob's part is the symmetric to Alice's part. So what we should do here is actually the copy of Alice's one. So Bob also measures his qubit on the X basis here. And in order to cancel the phase error here, if Bob tries to send this measurement outcome to Alice. But what is a good strategy of eliminating the phase error as much as possible? So this is done by looking at this property. So here, dominant contribution to the detection is a case where Bob emits single photon, odd number of photons, and Alice emits even number of photons, that is vacuum. So dominant contribution is combination of even odd and odd even. So the good strategy is to reset this number, reset the this qubit for the case where even odd and odd even. So this is a kind of a strategy to do that. So if you do that, then the combination of even and the combination of odd will result in a phase error here. So in this case, phase error happens when Alice and Bob both send even state or both send odd state. So the estimation of phase error probability is conceptually very easy because you only have to estimate the detection rate when this particular state has been sent to the central station. And actually the rate of this state and this state is also fixed due to this signal property. So only thing you have to do is estimate the detection rate of this single mixed state. This is conceptually look very simple. But the caveat here is that you can do the estimation by only using lasers, by only using coherent state. So this is where the complication arises, and there are so many proposals to do this in a symptotic regime. And if you want to a finite size solution, then if you like the simple solutions, then somehow there is a technique to reduce this to a classical sampling. You can do that. Or if you're greedy about the key rates, then you can use some improved version of azimuth inequality to obtain finite security of this protocol. Okay. So the next protocol is round robin DPS QKD. So I chose this protocol because I want to emphasize this property. So this approach is based on complementarity, and in some sense, this protocol highlights that kind of property here. So in this round robin protocol, Alice is going to use block of L pulses like this. And above, make a measurement on the whole block of L pulses using a delayed interferometer here. So this delayed interferometer chooses the value of delay randomly, uniformly randomly between all the combination of delays here. Then Bob has a detection at some timing here. So if Bob detects photon at some timing here, then Bob knows the phase difference between third pulse and fifth pulse. Okay. Then Bob tells Alice the number 3 and 5. Then Alice consults her record of the phase of the third pulse and fifth pulse, then takes the sum of them. Then this makes the Alice's shifted key bit. So obviously this bit and this bit should coincide if everything is ideal. And today I would like to make an assumption, which is technologically difficult, but for the sake of argument, I assume that total number of photons in L pulses is no larger than some integer nu. Nu is much smaller than L. And also, instead of this variable delay, I assume that this guy somehow rearranged the order of pulses in a cyclic way. Okay, so under this assumption, the security is proved like this. So here, each shifted qubit is generated from a bunch of L qubits here. So you must first write down this quantum circuit. But this is just, say, hearing the Bob's announcement here. Alice just pick up third qubit and J's fifth qubit here. Then plug into the control NOT gate. Then measure this qubit. Then this gives the shifted qubit for Alice. So this is what Alice does. And we ask what happens in X basis. So now the assumption that this pulse sequence is very weak. So the promise that the number of photons is no larger than nu means that if you look at these qubit states, no more than nu qubits are in state minus here. So this minus state is rare here. And in order to help to reduce the phase error, Bob switching from this real measurement to this measurement. So instead of doing phase measurement, just Bob does the which path measurement. So if Bob detects photon in this path, so this means that this number 5 is just determined from this random circulation. So nothing to do with input light. So this number 5 is uniformly random over L-1 values, except 3. And because minus state is limited here, and the J, this index J is chosen uniformly random, the chance of this state being minus state is actually L nu over L-1. So this is small. So probability of phase error is small. And what happens if Bob detects photon in this line here? In this case, J is no longer random. So there is a high probability of having minus here. But In this case, Bob tells Alice that Alice must do something. Then what Alice should do is applying the control node operation here. So this is one of the z-axis rotation for this qubit. So this is a route operation. And this quantum circuit can be rewritten using swap gate like this. So this effectively changes the role of I and J. So again, because I state index I is chosen uniformly random, and this control node gate does not propagate the phase error from here to here. So the probability of phase error is also bounded like this. So we conclude that phase error probability is this small number. So asymptotic key length is given by this quantity. And now, important point here is that this phase error is actually constant. This has nothing to do with Eve's attack. So this means that in this protocol, say this part, Eve's attack part, this has nothing to do with quantum mechanics. So Eve has only a small chance to read out the bit just because the signal is weak. So this is contrasted with a conventional QKD in which the focus is on this part. So any measurement leaves a trace. This is quantum property. So normally we think that the quantum mechanics coming in this part. But in this protocol, there is no quantum property here. So only place where quantum mechanics coming in is Bob's part. And that is the property of complementarity I have shown you in the first half of the tutorial talk here. Okay, and the last protocol today, and not least, is a continuous variable QKD. So CV-QKD uses homodyne detection or heterodyne detection. And this detection scheme has many advantages, as we heard on the invited talk on Monday. And for example, photodetector is cheaper than the photon detector, or this measurement has a very good mode selecting ability. So this measurement can filter out any different wavelengths or different timing straight lines. So CV-QKD seems to be good, but actually this area of QKD was off limit to the phasor approach. However, today I'm happy to announce that at least we can prove the security of CV-QKD, one type of CV-QKD, by using phase error correction approach. So the protocol is two-state. So kind of one of the discrete modulation protocol, the two-state CV-QKD, which uses exactly the same signal state as a B92 protocol. So just plus alpha and minus alpha. The difference is that we're going to use homodyne measurement and heterodyne measurement here. So in this particular protocol, for the signal, Bob uses homodyne measurement, and for the test, Bob's going to use heterodyne measurement. Now let us compare this protocol with the B92 protocol. And if you recall the B92 protocol, actually the B92 measurement here has two roles. So one role is on the signal part. So from the signal part, this measurement can select out only favorable events. So this measurement returns 0 or 1 only when, say, this measurement is sure about the outcome. So if the outcome is uncertain, then this measurement returns failure. So this is very helpful to improve the key rate. But for this point, say the heterodyne measurement here can, say, imitate this kind of function in up to a certain limit. For example, this is the outcome of the homodyne measurement. And the plus state would be around this, and the minus state is around this. So if you see this outcome here, then you will be pretty much sure the state is plus. And if you obtain this outcome, then you are pretty much sure that bit is 1. But if you have outcome here, then you are not certain about the bit value. So in this case, you can always define it's a failure. So this red curve here is a kind of acceptance probability. So by this way, for the signal part, somehow this CV measurement, homodynamic measurement, can mimic the B92 scheme. So having said that, okay, look at this template again. So here, the CV measurement is applied here. So what should we do here? So signal is the same as B92. So what Bob should do is distinguish even number state and odd number state. So in this case, you can directly use parity measurement of the photon number here. This is because as long as this function, this acceptance function here is an even function, so fixed parity function here, then failure measurement observable or operator commutes with even photon or odd number photon observable. So you can assume that Bob could have done this parity measurement here. So up to this point, it is okay. But in the case of B92, actually, you have to do this kind of, phasor analysis of phasor probability. And here you have to use the observed amount of bit error to determine the phase error, right? And this is what is lacked. What CV measurement lacks. Say in the case of B92 protocol, this measurement in the test mode, this measurement gives the estimation of bit error probability. So this is the second row of this measurement. In the test mode, this gives us the bit error probability. But if you look at this, this probability is equivalent to estimate the fidelity of received state to the ideal state. So the zero state should be arrived at this point as a plus beta state. So this bit error probability measurement by B92 measurement actually tells you about the amount of fidelity here, how close this quantity is close to 1. And problem in the CV measurement is you cannot obtain this fidelity. But somehow we found to do that by using heterodyne detection. So trick is here. So assume this function, this is function mu, which is composed of associated Laguerre polynomial like this. So if you plot this function, this depends on parameter m and r here, it looks like this function like this. Then we can prove that, suppose that omega here is the outcome of heterodyne measurement. So this is some complex number of the outcome of heterodyne measurement. Then input this square of this quantity to this function. Then take an average or take an expectation value when the state rho is input to this heterodyne measurement. Then we can prove that this expectation value is always smaller than the fidelity to the vacuum state. And lucky thing is that this is fairly tight. Actually, the equality holds if this state low is weak. If this state low has m or fewer photons, then actually this inequality saturates. And you can, if you can say about vacuum states, and you can just move the position of the origin to beta, you can also measure the fidelity to plus beta state and minus beta state. So this means that you can obtain exactly the same thing as a B92 protocol, which is a bit error probability or fidelity to the ideal state by using heterodyne measurement. Okay, so this means that you can do not exactly the same, but the similar kind of analysis here. You can prove the security of the CV protocol. Now, because this new function here is bounded, so for example, this purple curve is bounded from here to here. Because this is bounded, actually you can prove finite size security using Asma's inequality. And because actually phasor approach is always good against the general attack, so this proof is against general attack. And also because this function is smooth, so you can always incorporate the finite measurement precision. And also this is two-state protocol, so already it's a finite constellation. Maybe only drawback is that the key rate is not so good. And maybe this is because we are only using two-state. So except for this, actually, as a security proof, this has a very many good properties. So I'm pretty much satisfied as a first attempt from the phasor approach to the CV-QKD. Okay, so this is the end of the tour of the various quantum protocols. So I shall stop here and I'm show you the main menu, today's menu again, and I would answer if there is questions. Okay, thank you for listening.
Okay, thank you very much, Masato, for a very nice tutorial talk. Let's go to some questions. And there's already one in the question and answer, but encourage all the attendees to maybe also ask some questions there or raise your hand in the Zoom if you want to ask a question live. And let me start with the question and answer. I think it's referring to the slide where you showed the relationship between privacy and secrecy. So where you had that if you have delta secrecy, you get a square root 2 delta privacy condition for the other party. And the question is, how can one combine this type of analysis with the finite key decoy state method? So is there also a square root relationship between the failure probability of the decoy state estimation and the secrecy parameter?
Okay, well, I should go back to okay, so decoy state is about, say, BBA protocol with phase randomized laser pulses. So in that case, you have a tag of photon number. So Alice can have a record of how many photons she has emitted. And of course, and then using this tag, in the asymptotic case, you can divide the rounds to different things. So the question is, say, okay, so how to handle the finite size security here? Okay, so basically it's to make this kind of statement. So using the gathering the data obtained by measuring the decoy state detection frequencies, then you can analyze that, say, how much rounds it's a multi-photon part and how much is a single photon part, and basically you do that in such a way that you can give this kind of statement. So the question is whether square root relationship is applied here, but the square root relation is always here. So only thing you have to do is to solve this problem of decoy state statistics, so which is just a separate problem. So this has nothing to do with this part. So you can always concentrate on rephrasing the decoy state statistics into the form of this type. Then if you do this, if you find this number here, then you can convert to the epsilon secrecy of the protocol. So square root formula is always can be used. So difficult, maybe complication in the analyzing the decoy state finite size. It's somehow you can convert the estimation problem in the decoy state case to formulate in terms of the number of phasor patterns like this.
Okay, thank you for the answer. There's a second question now that is, I think, mostly a question about a reference. You mentioned that you can use any two universal function for privacy amplification. Is there, or where can one find a rigorous proof of this in the complementarity approach? Or is there a rigorous proof of this in the complementarity approach?
Oh, I see. So, okay. So I don't have a reference in this slides, but actually this was done by Dr. Tsurumaru here with Professor Hayashi. So if you, for example, if you look at this paper, then surely this paper has a reference, and you look for the paper by Tsurumaru and Hayashi. Then that paper actually discusses the relation between universal two functions in Z basis and X basis.
Okay, thank you. And one more question here is it also possible to use these protocols in a two-way quantum communication scenario? So I think with, yeah, it's explained like as a dialogue with forward-backward communication.
Okay, maybe honest answer will be I'm not so sure about that, but my guess is, sorry, my guess is that sorry. This general recipe will work in that case if you can use the property of two-way communication to bound the number of phase errors appearing in here. So even in that two-way communication, eventually Alice makes her shifted key, which is plugged into the privacy amplification. So you can always define qubits corresponding to the shifted key. So the remaining thing is to analyze the phase error occurring in that qubits. So that analysis may be quite complicated if you consider the ping pong type of communication. So actually, conceptually, I think this can be applied, but practically, I don't know if you can obtain a good key rate or not.
Okay, thanks. We have one question here in the chat, which is...
Yeah, actually, I was asking this question.
You can ask this.
I was just wondering, can you also analyze the 6-state protocol with this approach? So far, you always talked about one or the other basis. Can you also incorporate a third one?
Okay, how should I say? Okay, the 6-state protocol is a kind of tagging. If you agree, say the point crux of the 6-state protocol is that you have two different phase error probability. So one is the case where the Alice's bit value and the Bob's bit value coincide. And the second case is that Alice's bit value and the Bob's bit value, shifted key value, is different. So depending on whether the bit error occurs or not, actually the phase error can be different.
I see.
So in order to analyze 6-state protocol, you somehow make your protocol such that you obtain this tag, which corresponds to there is a bit error or there is no bit error. And the problem is how to extract that information as a tag. And that can be done by, oh, maybe it's so it is difficult to explain only by word, but actually this kind of tag can be obtained by applying, okay, so maybe best one is BB84 one. this is not, maybe this is not good, but so in the case of 6-state protocol, Bob also has a qubit, right? So Alice has a qubit and Bob also has a qubit. And in order to obtain that tag, actually only you have to do is that apply control not gate from here to here. Then z value of this is actually bit occurrence of bit error. So this becomes tag. And that operation, if you look at on the phase basis, then control not operation from here to here. Mm-hmm. And this is actually the correction operation. So by doing the rotation here, so in this BB84 protocol, I explained that Bob make a measurement here, then instruct Alice by using classical channel, then Alice rotates this. But instead of this, you can do the same correction by applying control not gate from Alice's qubit to Bob's qubit. So that control operation actually do this rotation, and at the same time, the qubit left by Bob, it becomes tag. So if you measure that qubit on a z basis, then that gives you information about whether a bit error occurred or not. So by doing this, actually, you can analyze the security of 6-state protocol in this framework.
Okay, thank you.
Okay, very good. I don't see any other questions. Oh, wait, there's, I think one just popped up. Okay, let's do one last question maybe. Is it true to mention that the main advantage of this approach is on DV QKD protocols in comparison with CV QKD? So I think that refers to the complementarity approach, I think. So there is the main advantage on discrete variable QKD instead of continuous variable QKD?
Yeah. So I would say until last year, actually, there is no way to prove the security of CV-QKD using this approach. So completely, we gave up completely. But this year, we happen to find one instance where this approach can be applied to the security of CV-QKD. But of course, that doesn't mean that this approach can be applied to any protocol of CV-QKD. So it will be interesting to say how far this approach can go in the field of CV-QKD. But one advantage is once we can establish the security, in this approach, it's easy to do the finite key analysis. That's one advantage. But of course, everything is heuristic, so you can heuristically find this kind of protocol. So compared to the mean entropy approach, say key rate tends to be lower. Mm-hmm. So that might kind of barrier to explore the CV-QKD, because CV-QKD is a kind of delicate balance between the errors and the gains and loss. So if we have a suboptimal way of doing that, then we might lose everything. That is a concern about applying this approach to the CV-QKD. But okay. We'll see.
Okay, thank you very much.